So this is where we left off the other day. We were talking about the role of mass, okay, and in inertia and in Newton's first law, okay? So mass has to do with how much matter is possessed by an object, okay? If we're talking about a person, it's how much of you there is, right? The more mass you have, the more inertia you have, okay? I mean, you think about sumo wrestlers. When's the last time you saw a skinny sumo wrestler? Okay, you can't win as a skinny sumo wrestler. Sumo wrestling is all about inertia. How hard is it to push somebody around? The bigger you are, the harder you are to push around. Okay, that's why there aren't little skinny sumo wrestlers. They're all really big guys because they're hard to move. Okay, and it's all about pushing the other guy out of the ring. Okay, so if we're looking at these two objects here, obviously there's not a whole lot of matter in a penny. We don't even have pennies anymore. Okay, but there's not a lot of matter in them. Okay. They're small. Whereas a super tanker that's completely full and has cargo packed on the top of it, okay, has a lot of matter, right? So it has a lot of inertia, okay? That's why it needs such big engines to get it going, right? Because there's a lot of mass to move, all right? Now, mass is a scalar quantity, and thus, so is inertia, okay? Your inertia is a scalar quantity, okay? We don't imply direction to something like that. Okay, questions on what mass is? Okay, so are mass and weight the same thing? They are not, okay? But this is another societal error that's been propagated for a long time. When someone asks you how much you weigh, you don't tell them how much you weigh, you tell them your mass, because that's what we've been taught that number is, okay? You step on the scale and it goes, get off, get off! No, it doesn't usually, okay? Usually it doesn't say that, unless I stand on it. But, okay, it'll tell you a number, but that number is in pounds or kilograms or something like that, okay? And that's your mass. Okay? The best way, if somebody actually, asks you that incredibly rude question, how much do you weigh? Tell them. I tell people how much I weigh. I tell them I weigh 775 newtons. They laugh awkwardly, look around for someone else to talk to. And then I get to feel okay because first off, they were an idiot. That's not something you should ask someone, okay? And secondly, I don't have to engage in any more awkward social play with them because, well, they shouldn't have asked me that question. But I also didn't lie, okay? I told them absolutely the truth. That's how much I weigh. Weight is a force, okay? It's not in kilograms. It's not in pounds, okay? Tell them what you weigh in newtons. Multiply your mass by 9.81 and tell them that number, okay? That's how much you weigh. Weight is the force of gravity acting on your mass, okay? So yes, the more mass you have, the more weight you have, okay? But there are situations where you can be weightless and still have mass. Everybody okay with that idea? So when you go and you work out, you're not lifting weight. You're lifting mass. Doesn't sound as cool, but that's what you're doing, okay? Now granted, okay, if you went up to the International Space Station and brought a bunch of weights with you, what good would it do? None. You wouldn't get much of a workout. They don't come back. In fact, if you got a bunch of stuff on a bar and you're about to do some bench press in zero gravity, you'll look really cool for about a half a second because you get that bar moving. No problem. The problem is now you can't stop it. Okay? Because now it's got all this inertia, just pull you right off the bench and off you go with it. Okay? And you'll look really stupid trailing behind this big bar. Okay? Yeah. All right, so lifting weight in space doesn't do anything because there's no weight in space. There has to be a gravitational field to give something weight, right? So that's why Bowflex and that kind of thing was invented. It was actually initially designed by NASA as a workout tool that astronauts could use if they were going to be in zero gravity for a long time. It doesn't require weight. It requires just resistance, okay? It was one of the things they discovered, that long-term weightlessness is really, really bad for the human body. Okay, all kinds of rotten things happen to your body in zero gravity. Okay, that was actually what most of Chris Hadfield's research was about. Okay, was the effects of zero gravity on the human body, and they're not good. Okay, the main thing that you can do to overcome that is exercise. Okay, but exercise is difficult in zero gravity. Most of our exercise depends on us moving our weight around. Okay, not our mass, our weight. Working against our weight or additional weight or whatever. So NASA had to come up with other ways to have astronauts work their muscles, okay? Not just their, kind of skeletal movement muscles like their biceps and their hamstrings and things like that. Certainly those were important, but also the muscles that help us to ventilate our lungs. okay? The little intercostal muscles between your ribs, okay? Your diaphragm, that muscle that sits underneath your lungs and changes the pressure inside your chest cavity. All of those muscles deteriorate in zero gravity, okay? So they had to devise ways that they could work them in a zero gravity environment. So they built like a special bike and a special treadmill, right? Now imagine trying to run or ride a bike in zero gravity. Okay, you push on the pedals in zero gravity, you fly off the seat. You try and run on a treadmill and you push and you fly off the treadmill. So they have these life preserver looking things, okay, like a harness that's attached by bungee cords, okay, to the bike and to the treadmill so that you can run on the treadmill but not fly off of it. Okay, they look pretty silly, okay, but the bike is the one they use the most because the bike is more practical. As long as you're like attached to it, it would be the same as on Earth. Yeah, it's the fact that if you're not attached to it, you fly off of it, right? There's no way to, when you push, it pushes back and off you go, okay? On Earth, when you're doing that, yes, you move a little bit, but your weight is big enough that you don't fly off the seat. All right, so weight is the force of gravity acting on your mass, okay? We calculate weight by doing this. Weight is the force of gravity, okay? And we calculate it by taking our mass in kilograms and multiplying it by the acceleration due to gravity. On Earth, that number is 9.81 meters per second squared on average. Okay, it isn't that much everywhere, but that's what we say it is for simplicity's sake. Right? This is just a variation of Newton's second law, which we'll talk about later. Newton's second law is force equals mass times acceleration. Okay, so the more I want to accelerate any mass, the harder I have to push, is basically what Newton's second law says. Okay, if you want a small acceleration, you don't have to push very hard. If you want a big acceleration, you have to push very hard. All right, that sort of makes sense to everybody? Okay. So to understand Newton's first law, think of like hockey or curling and imagine the ice is perfectly frictionless. Okay, if a player doesn't hit a stationary puck, it will remain at rest on the ice, or curling rock. Okay, if after the puck is struck, however, it coasts on its own across the ice, slowing down only slightly because of friction, or if it was frictionless, it would just keep going. Okay, in fact, if it were possible to remove all the friction and wind resistance and the rink were infinitely long, the puck would coast forever in a straight line at a constant speed. Okay, if that were the case. Now, obviously, it's not possible to do that, but if we could, that's what it would look like. Or it would look like Woody floating away, okay, in the clip that we watched there before. Okay, so if I'm a hockey player and I hit that puck, okay, how long does it accelerate? Not until it stops. As long as I'm hitting it, right? Okay, I can accelerate that puck as long as I'm exerting the force on it. Okay, so as soon as the puck leaves the stick, now it can't accelerate anymore because now there are no forces. Newton's first law governs all the situations where the forces add up to what? Zero. Okay, Newton's first law deals with all situations where our net force, okay, and that's what we're talking about here is our net force, okay, where F net equals 0 newtons. Okay, so net force works like your paycheck. All right, if you've got a job, right, you got your gross pay, which is usually like a nice big number, right? Then there's all the government extortion, taxes, CPP, EI, okay, all that kind of stuff that we pay, okay? And then after that is this sad number that is your net pay, okay? So net is what you have left after all the other things have been taken into account. So if I have, let's say, a box, okay, and it's sitting on a table, gravity pulls down, let's just say with 5 newtons worth of force, the table pushes back up with 5 newtons worth of force, which is why the box doesn't jump off the table. Okay, those two forces cancel. All right, let's say I push forwards with 6 newtons and friction resists with 4 newtons. What's the net force here? 2 newtons to the right. Okay, so this object's going to, it's going to not just move to the right, it's going to accelerate to the right because the net force isn't 0. If there's 6 newtons worth of friction, what happens? It doesn't move at all. Okay, it would be like having a really big, heavy object that you're pushing on that won't move. Okay, you can't overcome friction, so it just stays put. Okay, there's forces acting on it, but they all add up to 0. Everybody okay with that? Right? It would be a similar situation if you've ever used the cruise control in your car. Okay, the cruise control makes sure that the net force acting on your car is 0. That way it maintains a constant speed. If you start going up a hill, gravity becomes a bigger component. So the engine works harder, applying a force forwards to counterbalance it and keep you moving at a constant speed. Right? So the purpose of your cruise control is to maintain a net force of 0 on the car. All right. So an object at rest will remain at rest. That's the first part, okay, of Newton's first law. Okay, and an object traveling at a constant velocity, or will continue to do so until acted upon by a net force. And we should cross this off. It shouldn't be speed. It should be velocity. Because do I need to apply a force to turn something? Yes. Okay. I might not alter the magnitude of its velocity, okay? But to turn something, I have to apply a directional force in the direction I want it to turn. Okay, so this term, net force, is the vector sum of all the forces. This is what we looked at on the last page. Okay, when I drew that box sitting on the table, okay, we looked at the vector sum of all the forces. The forces up and down added up to 0. The forces left and right added up to 0. So the net force was 0. Okay. If we're looking at this situation here, okay, I have a net force of 2 newtons because force 1, which is 20 newtons left, is 2 newtons bigger than force 2, which is 18 newtons to the right. Okay, so this object, book or whatever it is there, is going to accelerate to the left. Okay, its acceleration will be dependent on its what? Okay, partly on the force and partly on its mass. Okay, the bigger the book, the smaller the acceleration will be. All right, so Newton's first law is what makes it possible to do things like this. Okay, if you had a stack of like poker chips or checkers or something like that, okay, and you flicked one at the bottom of the stack, if you hit it just right, you could knock out the bottom one and the stack would just drop and not tip over. Okay, because the stack of chips, okay, would have inertia saying we're going to stay put. If the force only acts on the bottom chip, then they don't move from side to side and they just fall down. Similar, if you've ever seen someone pull a tablecloth out from underneath all the dishes on a table. Okay, to do that right, many things need to come together, most of them involving technique. Okay, because most people, when they try to do that, they grab the tablecloth and they pull like this, and everything breaks. Okay, because when they do that, they're pulling upwards on the tablecloth, which lifts everything on the table and everything's broken. Okay, if you're going to do that trick properly, you actually grab the tablecloth and push it against the edge of the table and downwards. That way the tablecloth slides straight towards you. Okay, instead, and then hopefully if it's, you know, a very slippery tablecloth and all the dishes are quite heavy, then they won't tip over. Right? You wouldn't want to try that with a cloth tablecloth. It simply won't work. Okay, you need one of those really cheap dollar store ones for picnic tables that are vinyl. Okay, because they're really slippery. Okay, and if you're gonna try it, buy a bunch of plastic dishes. Okay, do not put Mom's Best china and crystal on the table and go, "Hey, Coderre said no, I didn't." Okay, I did not say that. All right, but you can do it if you have this set up properly. Okay, Newton's first law says that as long as there's no net force acting on those dishes, they shouldn't go anywhere. Obviously, there's going to be some force. There's going to be some friction there between the tablecloth and the dishes. But if you do it right, okay, then it won't break. It's the same for like ripping toilet paper off a roll. Okay, you can either hold the roll and pull, or you just pull really quick. Okay, it'll tear along the perforations and the roll won't unravel. You can try that one at home, because the worst that can happen is you unravel the whole roll of toilet paper. Okay, making sense to everybody? Yeah? All right, so a net force that can cause a bicycle to pick up speed quickly, okay, may not have the same effect on a freight train or a car or a plane, okay, because those planes, trains, and other automobiles may have, okay, too much mass for that force to do anything to them, okay? So as we said, okay, mass and inertia are dependent on each other. Essentially, they're the same thing. Okay? An object's inertia is dependent on its mass. Okay, so like we said, quantitatively, the inertia of an object is measured by its mass, such as that of the train indicating a large inertia. So inertia is the natural tendency of an object to remain at rest or in motion at a constant speed along a straight line, okay, or a constant velocity would be a quicker way to say that. The mass of an object is the quantitative measure of its inertia. That's Newton's first law stated out. Okay. All right, so like we were saying, Newton's first law is the thing that most of your crash tests or your crash and safety devices in your car are trying to prevent. Okay, they're trying to prevent Newton's first law from carrying you into a place where you could be injured. Right? They're trying to keep you with the car, make you part of the car's mass, limit your acceleration, okay, and thus limit the forces acting on your body. Okay. In fact, seatbelts use this in order to catch, okay, because it's infallible. Okay, there's nothing we can do to stop Newton's first law. Okay, so your seatbelt works with a pendulum. Right, so I mean, you've all gotten in your car, right? You're in a terrible rush, and you grab the seatbelt, and you grab it too quickly, and it catches, and then you're like, and you're in such a rush that you just can't let it go back enough to let go. Okay, we've all been there. How it works is if you jerk it really quickly, usually what happens is you just jerk the whole assembly enough that the locking bar catches on the ratcheted wheel. Right? In a crash, what happens is instead of the pendulum hanging here, straight up and down, which is what it does while you're traveling at a constant velocity. Okay? If your car stops suddenly, the pendulum continues to move forwards, swings forward, and when it pivots, it lifts the locking bar so that your seatbelt can't unravel. Okay? It catches in there. Right? It doesn't rely on any electronic sensors that could get messed up or anything like that. It relies on an absolutely infallible physical law. Okay? And so it will work every single time. All right, that sort of makes sense to everybody? I mean, that's how they work now. Okay? Back in the day, you just like resized the lap belt and hoped that it didn't give out when you got in an accident. That was the only place you were attached. Okay? But now, obviously, they're much better than that. Okay. All right, so we're going to just look at free body diagrams here, just so we understand, because I've drawn a few. Okay, free body diagrams are drawn not with the actual object. Okay, because well, I'm not an artist and it takes too long to actually draw pretty pictures. So whenever we draw a free body diagram, the object is represented by a box. Okay, and you write the mass of the object inside there. Right. So in this one here, they didn't even tell us the mass on this, and we'll just say it's 1,500 kilograms or something like that. Okay, so we would draw all the forces acting on the car as though they act out of the center. Okay, so this would be the force of gravity. Okay, this could be the force of the engine or the applied force. Okay, there'd be a force of friction here. Okay, and then there would be the force of the ground, which would be equal to the force of gravity. All right, unless the car was somehow jumping off the ground. Okay. Everybody all right with that? Okay, so as long as the applied force is bigger than the force of friction, the car is going to not just go forward, accelerate forwards. Okay, if these two forces are equal, what are the two things the car could possibly be doing? Moving at a constant velocity or not moving at all, which is still a constant velocity of 0. Okay, so those are essentially the two situations that could happen if the net force in that situation was 0. Okay. All right. You know, I think that's all we need to look at for that one. Yeah. Okay.